Hello everyone, welcome to online lecture series of electronic devices. The subject code is KEC301. This is lecture number 20 and today's topic is VI characteristic of PN junction diode. Before starting this, let me introduce myself. I am Dr. Sapna Katiyar, Professor in Electronics and Communication Engineering Department at ABES Institute of Technology, Ghaziabad. Let us begin today's topic. So, here I will be discussing about the VI characteristic of a PN junction diode, diode approximations, VI characteristic of ideal diode. You must remember, you can draw the VI characteristic for a practical diode as well as for the ideal diode. In your examination, if you are getting a question, draw and explain the VI characteristic of a PN junction diode, it means you have to draw the practical curve. Then I will be discussing about the effect of temperature on the VI characteristic. What is the effect of temperature on the characteristic and the diode resistance? There are two possible types of resistances which you can calculate, AC resistance and DC resistance. So, both the resistances we can also calculate. So, let us begin with the first topic, which is the VI characteristic of a PN junction diode. Now, just try to recall what we have discussed in the previous lecture. What is diode? Diode is a two-terminal device. There are two terminals in this particular component, two electrodes it is having. Diode, two electrode, one electrode is anode, second electrode is cathode. So, diode can be used as a circuit element in any electrical circuit as per the requirement. So, you must understand how it behaves when you are going to connect it in any circuit. Means connection may be in the forward bias depending upon the battery, it may work in the reverse bias condition. So, accordingly you have to explain it, and such type of information can only be obtained by a curve which is known as a voltage current curve or VI curve of a practical diode. As we have already discussed, if there is a addition of the external voltage, external battery, that battery can be connected in two manner. Accordingly, the two biasing conditions may possible. One condition is the forward biasing. So, in that particular condition, you can plot the characteristic curve. If you reverse the polarity of the battery, then it will work in a reverse bias condition and the reverse characteristic can also be plotted. So, the complete characteristic curve, VI characteristic curve, can be subdivided into two parts. One is the forward characteristic and the second is the reverse. So, in both these situations you have to plot it, then it will be a complete curve, right. Before moving further, let us discuss the applications of a PN junction diode. As you know that this is very important device, very important component, you must understand its behavior because it is being used in a number of applications. So, what are those applications? You can note it down. Diode can be used as a rectifier. Rectifier converts the AC into a pulsating DC. Diodes can be used in clamping circuit where there is a requirement of DC level restoration. It can be used in a clipping circuit. Clipping circuit means for wave shaping, positive half, negative half, or some of the portion can be clipped off depending upon the requirement. It can be used in a voltage multipliers, it can be used in voltage regulators, in a switch, as a switch in digital logic circuits, in demodulation circuits, laser diodes, LED diodes, even in a number of toys nowadays. You used to see because there are the application, there are the use of the LEDs and all. So, PN junction diode is a versatile component, can be used in a number of devices, right. So, on the basis of this you can write down, you can list the applications as well. Now, let us discuss about the forward characteristic curve of a PN junction diode. How to plot the forward characteristic? Forward characteristic means when a PN junction diode is in the forward bias condition. When it will be in a forward bias condition? When P type semiconductor terminal, P terminal is connected to the positive and N is connected to the negative. Now it is in the forward bias condition. You can see in this particular diagram, this is the external voltage which you have applied. This is the P type semiconductor, N type semiconductor, and this is the junction. When you are joining, initially diffusion process will take place because of the concentration gradient. After a certain time across the junction, there is a formation of depletion region. The depletion region which is having uncompensated positive and negative ions, uncompensated acceptor and donor ions. Now, what will happen, as we have discussed, if you are increasing this potential, this voltage V, what is going to happen? See, this is the positive terminal of the battery, this is the negative terminal. When you are increasing this voltage, now holes which are in the minority, they will be pushed towards the N, and electrons which are in the majority in N region, they will be pushed towards the junction. Means holes are in the majority over here, electrons are in the majority over here. Now these holes and electrons will be pushed, they will cross the junction, recombination will take place, and this depletion layer width will decrease. It means what is going to happen? Until unless this applied voltage is not overcoming that barrier potential, only a small amount of current flows. See, what is barrier potential? When depletion layer is formed, now what it does? It will further stop the diffusion across the junction. Because of this, a restraining force is set up. And you can see over here, this is the negative terminal, this is the negative ions, positive. When the applied voltage overcome this particular potential, then only further diffusion recombination will take place. And if we are talking about the silicon semiconductor, if the silicon semiconductor is used for the manufacturing, then in that particular case, this barrier potential is 0.7 volt. If the germanium is used, the barrier potential is 0.3 volt. It means when this applied voltage overcomes these values, depending upon the type of semiconductor, till that particular point, small amount of current flows. You can see in this particular diagram, VF forward voltage in the forward bias condition, IF current flowing through the diode in the forward bias condition. You can see initially a very small amount of current flows, but after this knee voltage, this VE, we can write it down. After this particular point, there is a sudden rise, and this particular value is 0.7 volt for the germanium, 0.3 volt for 0.7 for the silicon, this is 0.3 for the germanium. So, only a small amount of current flows. What is the diode current equation over here? You can note it down. The diode current equation can be written as I is equal to I naught e raised to the power V upon eta Vt minus 1. See, I is the diode current which is passing through the diode. I naught is the reverse saturation current, which is the leakage current. V is the external applied voltage which is being applied over here. Eta is a constant, and the value of this particular constant, eta is 1 for germanium and this is 2 for silicon. Vt is volt equivalent of temperature. This is nothing but K into T upon Q. K is the Boltzmann constant, you know its value. Q is the charge. If you substitute the value of K and Q, you will be getting Vt as it would be T upon 11600. So, this is the value of Vt, which is the volt equivalent of temperature. So, just substitute it and accordingly you can calculate the current which is passing through the diode, right. So, Vi characteristic curve in the forward biased. Similarly, you can plot the reverse characteristic when the diode is in the reverse bias. When the diode is in the reverse bias, when P terminal is connected to the negative terminal of the battery and N type is connected to the positive terminal of the battery. You can see over here, negative end is connected to the P terminal, positive is connected to the N. This is the junction, and after a certain time when a barrier potential develops, a electric field develops which will further stop the diffusion across this particular depletion layer. Now, what is happening? What is happening over here? When this voltage is being increased, V, see, when this voltage is being increased, holes will be moving away from the junction, electrons will be moving away from the junction. Now, this depletion layer will be increased, right. So, it means here in this particular case the current conduction is because of the minority charge carriers, not because of the majority charge carriers. Here minority charge carriers are electrons, here minority charge carriers are holes, they will be moving crossing towards the junction and the current flows. So, current is flowing because of minority charge carriers in a very small amount. So, you can see in this particular characteristic curve, VR is the reverse voltage which is being applied over here, IR is the current which is passing through the diode in a reverse bias condition. You can see initially a very small amount of current flows which is the reverse saturation current denoted by I naught, but if you keep increasing this particular voltage, what will happen? After a certain time you can see there is a voltage. If you keep increasing voltage, keep increasing, then there will be a sharp increase, sudden increase, means breakdown will occur, and the value of voltage at which breakdown occurs is known as a breakdown voltage, right. So, this is the breakdown voltage and this is how you can plot the characteristic curve. So, if you have to write down the diode current equation, just you have to write the minus V, because in the reverse bias minus sign is being included. I is the diode current, I naught is the saturation current, V is the applied voltage, eta is a constant, Vt is the volt equivalent of temperature. All the terms are same over here. So, this is how you can plot the characteristic curve in the reverse bias. If you join the forward and reverse bias characteristic curve, that will gives you the complete characteristic curve of a PN junction diode. VI characteristic curve of a germanium and silicon diode. See, germanium and silicons are the semiconductor. You know that if the silicon is used for the manufacturing of the diode, the knee voltage for silicon is 0.7, the knee voltage for germanium is 0.3, right. So, just both the characteristic curves have been plotted and have been compared over here. The reverse saturation current, if this is the forward characteristic curve for in the forward bias situation, this is the reverse curve in the reverse bias situation. Here you can see this current which flows because of the minority charge carriers in case of germanium diode, that is of the order of the microampere, and in case of silicon it is of the order of the nanoampere. So, you can imagine how small this amount of current is actually. So, this is how you can plot. So, cut in voltage I have told you, potential at which current starts increasing, this point, this is known as the offset potential, threshold potential or firing potential. Reverse saturation current for germanium is of the order of the microampere, for silicon it is of the order of the nanoampere, and breakdown voltage at which the voltage at which diode breaks down, there is a sharp increase, that particular voltage is known as a breakdown voltage. Diode approximation, this is the second topic. Diode there are three possible approximations of a diode which can be like applied, which you must remember. So, diode approximation, it is a mathematical method which is used to approximate the diode. Three different approximations as I have told you. The first approximation, here the ideal diode can be used as a first diode approximation is the case of the ideal diode. Here diode can be used as a perfect switch. If the diode is behaving as a short circuit means on. If the diode is behaving as an open circuit means the off condition, on and off. So, the switch is closed if the diode is in the forward biased means when it is conducting then the switch is closed, and in the reverse bias when diode is not conducting it will act as a open switch. Vt is the barrier potential. So, whatever the voltage being applied in the forward bias it will reflect across these terminals, right. So, the voltage whatever the voltage is being applied, this is the positive, negative. So, this is the first diode approximation. Second diode approximation, here the diode is considered as a forward bias diode in series with a battery. Why there is a requirement of a battery over here? To turn on the diode. You can see this battery, this potential is Vt, and whatever the voltage is being applied that will reflect in between these two, and this particular voltage must be greater than this Vt, then this diode will conduct, right. Third diode approximation. In the third condition, the internal resistance, diode resistance is also being taken into the consideration. You can see over here, here is a term of the bulk resistance Rb, this is Vt, and the applied potential will be reflected in between these two ends. So, you can, if the I is the current which is passing through this particular diode, IF let us write. So, you can write what is Vf. Vf is nothing but Vt plus Rb into IF. This is Vf. So, this is how you can draw all the three approximations, and depending upon the approximation you can draw the Vi characteristic curve as well, right. Now, see, as I have told you, in the ideal case, in the first approximation, what happens when diode conducts, and when diode conducts, when it is in a forward bias condition. So, in forward bias condition, when diode conducts, it behave as a perfect switch, and the condition will be closed, on. While in the reverse bias condition, when the diode is in the reverse bias condition, this diode is not conducting. When the diode is not conducting means it will be represented as a open circuit, open switch. So, this is how you can draw it, means you can explain how the diode can be used as a switch. During the forward bias, the closed switch, it will conduct. During the reverse bias, it will act as a open switch, it will not conduct. This is the characteristic curve of the ideal diode. You can see Vi characteristic curve of the ideal diode. The first approximation, just recall, in forward bias, even when the diode is being connected in any circuit, applied voltage is even if 0, it will start conducting. That is why it will start conducting. While in reverse, there is no flow of current. This is the closed switch, this is the open switch. This is the first approximation. If you have to draw the Vi characteristic curve for the second approximation, what happens over there? In that particular case, diode along with a battery, just try to recall it, diode along with a battery. And if the silicon diode, if we say the diode is made from the silicon, then this particular curve will be formed, V forward, I forward. While in third case, there is a bulk resistance which is also being taken into the consideration. So, in that particular case, the knee voltage will be 0.7 for the silicon diode, but because of non-linear behavior, it will represent the curve in this particular manner. So, this is how you can plot the characteristic curve for the ideal diode, and depending upon the approximation, first approximation, second approximation and third approximation. Now, what is the effect of temperature on Vi characteristic? If there is a change in temperature, what is the effect and its behavior right. See, an increase in temperature will result in a large number of breaking of covalent bonds, and since large number of covalent bonds will break, it means number of electrons and holes which are in the majority, they will be more number of minority and majority charge carriers will be available. So, they are going to impact upon the condition. And just try to recall the diode current equation. I is what? I naught e raised to the power V upon eta Vt minus 1. Here you can see the diode current I, it depends upon two factors. What are the two factors? The factors are temperature and leakage current. So, here you can see the two curves, different curves have been plotted. One is for the 25 degree, one is for the 100 degree. See, as if I have told you that if there is an increase in temperature, see from 25 to 100, more number of covalent bonds will break, more means higher the number of charge carriers, majority and minority. So, the current conduction will be before this particular point. So, cut in voltage is reduced. This is the voltage V1, this is the voltage V2. First you have drawn for 25 degree, voltage is V1. So, if the temperature is being increased, voltage will be reduced. This cut in voltage will be less. Here this value of V2 will be less than V1. So, cut in voltage reduces with the increase in temperature. It means for same forward voltage, large current flows at the increased temperature. Second, reverse saturation current increases with the increase in temperature. As I have told you, I depends upon two factor I naught and T. And the third, breakdown voltage is also increases with increase in temperature. You can see from this particular curve. So, this is how you can explain the effect of temperature. You can plot the various factors. Even if you decrease the temperature from 25 to 15 degree, the knee voltage will, cut in voltage will increase, right. Here this particular value, this voltage is higher than, right. Now, let us discuss about the diode resistance. Resistance term you are very much clear. How to calculate the resistance? You know the Ohm's law, V is equal to IR. From that you can calculate R. R is what? V upon I. When we are talking about the diode, it is being connected, it is being applied in any circuitry, then you must be comfortable, you must be aware with the terms which are related to the diode resistance. There are two terms, one is the static resistance. Static resistance is also known as a DC resistance. Second is the dynamic resistance. Dynamic resistance is also known as a AC resistance, right. Static or DC resistance, dynamic or AC resistance. What is a static resistance? See, static resistance, it is expressed as a ratio of DC voltage to the DC current at any particular point. You can see in this particular diagram, here a curve is being plotted. On the x axis voltage is being taken, on the y axis current is being taken. If static means fixed, if we have to calculate the static resistance at point A, if the value of voltage is V1 at this point, current is I1. Static means at any fixed point. So, what is the value of this resistance? Static resistance or DC resistance at point A, this is nothing but V1 upon I1. If you have to calculate the static resistance or DC resistance at this particular point B, if the value of voltage is V2 over here, value of current is I2. So, what is the static resistance at this particular point? RF will be V2 upon I2. This is at A and this is at B. So, this is how you can calculate the ratio of voltage to the current at any particular point, which will gives you the static resistance. Now, let us talk about the dynamic resistance. Dynamic means where there is certain variation, certain change. Dynamic resistance you can calculate it in any interval. See, It is given as the ratio of change in voltage, and because of that change in voltage, how much current is changing, that particular ratio will gives you the value of the dynamic resistance. Dynamic resistance is also known as a AC resistance, and you know that it is denoted by small r f. So, if you see in this particular case how to calculate it, if you are calculating the dynamic resistance while moving from A to B in this particular interval, in time delta t, if there is a change in voltage from V1 to V2, and because of this voltage, if there is a change in current from I1 to I2. So, you can calculate the dynamic resistance, which is Rf. Rf is what? This delta V upon delta I, and this delta V is nothing but V2 minus V1, and I is I2 minus I1. So, in this manner you can calculate the dynamic resistance or the AC resistance. Clear? DC resistance, static resistance, AC resistance and dynamic resistance. Now, some of the points which we have discussed and which you need to remember. See, application of PN junction diode. What are the application of the PN junction diode? You must be able to understand diode can be used as a switch, diode can be used in a rectifiers where there is a requirement of conversion of the AC into the pulsating DC. Diode can be used in a clipping circuit. Clipping circuit, from the name itself it is clear, to clip something, to clip off means removing something, some of the portion of positive, some of the portion of negative, or both, or anything. Diode can be used in a clamping circuit. Clamping means shifting, pushing the DC level. So, number of applications are there. LEDs, lasers, these are nothing but the diodes. There are three approximations of the diode: first approximation, second and third. In the first approximation, ideal diode can be used as a perfect switch, the first approximation. During the forward bias condition, diode conducts, and when diode conducts, it behaves as a closed switch. During the reverse bias condition, diode does not conduct, means the open circuit. Second approximation, here the diode is considered as a forward bias diode in series with a battery. You must remember it, in series with a battery to turn on the diode. When the applied potential in between the terminals will be higher than the potential of this battery, then diode will be on. The third approximation, the case is, it includes the voltage across the diode, and a bulk resistance is also being included for this case. It means diode along with the battery along with a resistance, and that resistance is the bulk resistance. Diode current equation, I have told you what is the diode current equation. I it is equal to I naught e raised to the power V upon eta Vt minus 1. I naught is the reverse saturation current, V is the applied voltage, eta is a constant, its value is 1 for germanium, 2 for silicon, and Vt is the volt equivalent of temperature, which is Kt upon Q. Substitute the value, you must remember it, it is T upon 11600 volt. Then static resistance or a fixed resistance or DC resistance, and it is the ratio. Static resistance you can calculate at any particular instant of time, right. So, at that particular point, whatever the ratio of voltage to the current, that will gives you the value of static resistance. The dynamic resistance, wherever there is a change, means in a certain time interval, if there is a change in voltage, and because of that change, whatever the change in current, so that ratio, change in voltage to the change in current, delta V upon delta I, that will gives you the value of the dynamic resistance. Dynamic resistance is also known as the AC resistance. This is also known as a AC resistance. Static resistance is also known as a DC resistance, right. And besides that, we have discussed about the VI characteristic of a practical diode and VI characteristic of a ideal diode. So, wherever you have to draw the VI characteristic, you have to analyze how diode behaves, how it conducts, how it works in a forward bias condition, what is its behavior in a reverse bias condition. So, by considering both the cases, forward and reverse, the VI characteristic can be drawn. So, ideal case you can also draw, and practical case you can also draw. So, all these things we have discussed in today's session. Thank you so much for watching this.